All right. So ada a bit of delay lah lagging. Okay, so we are. Is my microphone on here? Yeah. We are looking at question 32, part, the first part A. Okay, so you have, you are given cobalt chloride compound, ammonium chloride, and ammonia. These three can produce complex ions with the general formula CO, NH3, 6 minus N. I don't know if you can see that. ClN, 3 minus N. Okay, so that's the general formula for the possible complex ions being formed when you mix cobalt ions with the mentioned compounds just now. Determine the oxidation state of the cobalt in this complex ions. So which formula are we looking at is this complex formula, because that's the only complex ion mentioned here. The others are called just compounds, okay? So we want to know the oxidation state of the cobalt. Since we don't know how many, what our N is, we can just use any N equals to 1. Hazwan, where are you sitting? On a chair or on the floor? Okay. All right, since we want to work out the oxidation state of the cobalt, we can just use any N, okay? Any integer N, as long as it's between 1 and, I think it works with 6 as well. Yeah, between 1 and 6, okay? Not bigger than that. So if we just use N equals to 1, we should get cobalt with 6 minus 1 is 5. And Cl is just 1. Our overall charge would be 3 minus 1 is plus 2. So from here, we can work out the oxidation state of cobalt, where the sum of all the oxidation state or the charge of the ligands and the metal should be equal to the overall charge, which is plus 2. Okay, NH3 is 0. Chlorine or chloride is minus 1. Okay, so cobalt should have an oxidation state of plus 2 plus 1, which is plus 3. This works for any N. If you want to use N equals to 2, that's fine as well. N equals to 3. The oxidation state of cobalt will not be changed, even though the number of ligands change. Okay, so that's the idea of ligand exchange, where the oxidation state stays the same. Okay, name the two types of reaction undergone by the cobalt ions during the formation of these complex ions. So you can see that the number of ligands, the number of ammonia ligands and the number of chloride ligands can change in this complex ion depending on what your N is. So that means this reaction is called a ligand exchange reaction because the number of ligands can change. That's the easier one to spot, ligand exchange. Ligand displacement or ligand substitution. Yes, thank you. I forgot about that. The second reaction, however, is not as obvious. Do you see there's another compound with cobalt in the formula, COCl2? Can we work out the oxidation of cobalt in COCl2? Yes, cobalt is plus 2. Cobalt in cobalt chloride is plus 2. Cobalt in the complex ion is plus 3. So what type of reaction do you think that is? Oxidation. So That means cobalt also goes through an oxidation where the cobalt goes from +2 to +3. So that's not as easy to spot. Okay, that's all for question 30. No, Balom, sorry. Now I would like to go to B part 2 just to check that we know how to write the correct formula as well as working out the coordination number and ligands as well. Okay, so there are a lot of things that comes into play here. One, oxidation states. Secondly, the type of ligands. Is it a monodentate, bidentate, or polydentate? Another thing is coordination number. Let's start with the first complex C, where our metal center is chromium 3 plus. It's good. It's nice that they give us the oxidation number or the oxidation state. The ligand is the cyanide ion. This is a monodentate ligand where it only forms one dative bond per molecule of cyanide or per unit. Cyanide ions are also almost the similar size as ammonia and water. So it would follow the trend. Okay, so usually ammonia and water, what is their typical coordination number? 6. Okay, so we're going to try first. Try with 6 and we'll check our answer later on. Okay, how to write down the formula of the complex with the chromium ion. And then there are 6 cyanide ion. We need to work out the overall charge. The overall charge is given as 3 minus. However, we must also check if our formula is correct or not. Okay, so how do we check that? By checking the oxidation state or the oxidation number. Chromium is +3 as given. Cyanide has a charge of -1, and there are 6 of them. +3 minus 6 is -3. So that means our formula is correct. It matches with the charge on the overall charge on the complex. Okay? Okay. Next one, complex D. We've got a nickel with an oxidation state of +2 or a charge of 2 plus with what we call a ligand. This is 1,2-diaminoethane, another name, ethylene diamine. I don't know if anyone can already spot that this ligand is actually a bidentate. Okay, so bidentate, it forms two dative covalent bonds per molecule. Since there are 2 nitrogen atoms, well, it's not the rule. It's not always the rule where a molecule that has 2 nitrogen atoms will always be bidentate. No, there is no rule saying that. It's just something that you have to memorize, and sometimes they give you the hint in the question as well. Okay, so this is a bidentate ligand. And the complex with this bidentate ligand would have a coordination number of 6. That means 6 dative bonds. Coordination number is dative bonds, not number of ligands. Okay? So if one ligand form 2 bonds, how many ligands do you need to form 6 bonds? Only 3. Okay, so that means our formula of this complex would be nickel with the full formula of the ligand CH2, CH2, NH2, and only 3 of them. And the charge on the complex is something that we have to work out. Okay, let's work out the charge. Um, I would change the color, sorry. Okay, let's work out the overall charge of the complex. Nickel is plus 2. The ligand, does it have any charge? No. Okay, so here is again a good thing about this question that they tell you the formula of the ligand. Some question will require you to memorize the ligands, the formula, the structure yourself. Okay, so plus 2 plus 3 times of a neutral ligand, it doesn't have a charge, so it's just 0. Overall, you would get a plus 2. Okay, so that means your charge is 2 plus, or if you write down plus 2 is also fine. In this case, um, they accept both answers. Okay, don't forget to add the charge onto your formula. If you don't add it to your formula, that means your formula is wrong. This 2 plus must also be added to um, the column where it says formula of complex. Okay, so far? Okay. Next, complex E. We have a platinum 2 plus and a chloride ligand. What is the typical, we're testing first, typical coordination number for chloride ligands? 4. Just like your CuCl4 2 minus, okay? So I am just going to try first, 4. And to write down the formula, platinum with Cl4, and well, it says the charge on the complex is 2 minus. I have to check first, okay? Platinum is plus 2, and there are 4 units of chloride. Chloride has a charge of minus 1. 2 minus 4 equals to minus 2. So that means my charge is correct. My formula and coordination number is also correct. What is an example of a wrong answer? For example, wrong answer. You forgot that PTCl6. Okay, you thought that chloride would have an coordination number of 6 or an octahedral structure. Okay, so you check that PT is plus 2 as given. Chloride is minus 1. Each chloride ligand or each chloride unit is minus 1. So plus 2 minus 6 would be plus 4. And that doesn't match. Salah. I cannot do math. Minus 4. Plus 2 minus 6 is minus 4. So there's a mismatch. That means this formula is wrong. The coordination number 6 is also wrong. Okay? So it's good that you can check if your formula and coordination number is correct or not. So that means it is correct. The coordination number of platinum with chloride ligands is 4. Okay, next. For case step, so try to put the charge outside because it's the charge of the overall complex ion. If you put it inside, um, I'm not sure, Pulang. The problem is I'm not sure if it's correct or you will be penalized. I mean, technically it's correct, but I'm scared that they will penalize you. It looks like the yes, if case step you need to put inside because the number outside is for the power. You raise the concentration, okay? So when you write down the formula of the complex, you write the charge outside the square bracket, which indicates this is the charge of the overall complex atoms. Okay. Next, complex F is a carboxylate. Okay, so it's CO2. di CO2 minus. It is actually a bidentate ligand, just like your oxalate bidentate. Oxalate ion, and it is one oxygen on each side. There are two oxygen, but only one oxygen on per methanoate. Okay, so this is a bidentate ligand, and if you look at the formula is given to you, each molecule or each unit of the bidentate ligand forms two dative covalent bonds, and in the formula there are three molecules or three units. Okay, so that means the coordination number, the total number of dative covalent bonds will be 3 times 2, which is 6. Okay, good. Charge on the complex. Now this is where they are trying to trick you, okay? Because it says here the charge on the complex is neutral. Yeah? Well, it looks like it's neutral. There's no charge. Actually, I don't know if this is a misprint or they purposely do this to trick you, okay? Let's check the oxidation, let's check the overall charge of the complex ion. Fe is plus 3. There are 3 lots of this bidentate ligand. The charge of each bidentate ligand is minus 2. You just add up the negative charge, okay? So minus 2 plus 3 minus 6 should give you minus 3. That's right. Again, cannot math today. Minus 3. So overall charge on the complex is 3 minus or minus 3. Okay? When you write down, kalau charge, okay lah. Tapi kalau oxidation state, mesti sign first. Yeah. So, it's a bit confusing, right? So many things to remember. Just make it a habit to start with the sign first lah. For this question, they accept both. Okay? Yeah. Yeah, oxidation state. If you write down your oxidation state as 3 plus, that's charge ba? I think so. Charge is a bit, charge macam, they're quite flexible, but oxidation state is a bit strict. Okay? Okay. So I'll just leave that first. If you're done with that, we can move on to question. Question 36, part B. So case step. So usually when students look at case step, they go like, oh, because it is filled with a lot of alien language. Basically, just some complicated formula, complicated looking. But actually, this question is adalah a little bit complicated. Let's move on to question 36. Part B, okay? So cadmium ions, CD, form complexes with methylamine and 1,2-diaminoethane. So that's our bidentate ligand that we just looked at earlier. The 1,2-diaminoethane is shown as En. So here they use the short form or shorthand notation En, okay? Equilibrium 2 is when methylamine kicks out water. So this is a ligand exchange. It kicks out 4 water molecules out of 6. Equilibrium 3 is when En kicks out water. Only, again, 4 molecules of water, okay? Because En is a bidentate ligand. So that means 2 molecules of En would form 4 dative bonds, right? Okay, but That's not our concern now. When we mix this equilibrium 2 and 3, we will get a new equilibrium, which is called the equilibrium 4. It's a mixture of equilibrium 2 and 3. Okay. KEQ4, where K is the equilibrium constant for equilibrium 4, write an expression for the equilibrium constant of equilibrium 4 in terms of K step 2 and K step 3. Okay? Now, this only for 1 mark. I don't know how else to make this um, in a in a few steps, okay? But hopefully after I show it to you once, you will be able to see it or spot it straight away, okay? So the first time we do will be a long process. Actually, it's not long. Ganyan, the formulas are very very long. Yeah. Okay, we start with writing down the expression for K step 2 and K step 3. Okay? So K step 2 is the equilibrium constant of equilibrium 2 where products, concentration of products raised to the power of their mole ratio over the concentration of the reactants raised to the power of the mole ratio. And that's the same for equilibrium 3 as well. However, there is something that is being excluded here. Does anyone remember? Yes, the water is being excluded because in your notes, water is present in excess. There's water here. There's water in the whole mixture that you wouldn't be able to know how much water you have produced. Okay, so let's start with writing down the case step 2. My products. So this is where Daniel's question came in just now. We will now put in the charge of the complex inside the square bracket because the square bracket now represents concentration. The square bracket is no longer representing the formula. It's now representing concentration. So let's try to do that slowly so we don't leave anything behind. H2O2, 2 plus to the power of 1, since there's 1 mole. Okay? Okay, let's do together. Two plus goes inside to the power of 1 because there's only 1 molecule, times by the concentration of the other reactant, which is CH3NH2, this time to the power of 4. Okay? That's my case step 2. I move on to my case step 3, where I have the concentration of my products minus the water, CdEn2, H2O2, 2 plus goes inside over the concentration of CdH2O6 2 plus times the concentration of En to the power of 2. So the only number that goes outside the square bracket is the one with mole ratio other than 1. Okay. Once you're done with case step 2, case step 3, I now want to write down the equilibrium constant for equilibrium 4, where the concentration of products over the concentration of the reactants. You probably don't have enough space. You can use the bottom of the page, page 21. So I will use purple for equilibrium 4. I will take the CdEn2 H2O 2, 2 plus to the power of 1 times by CH3 NH2 to the power of 4 over the concentration of CD, CH3, NH2, 4, and H2O 2, 2 plus to the power of 1. Sorry, excuse me. Okay. En to the power of 2. I don't know if anyone can spot it. Can anyone spot anything? Okay, we go back to the question. Sorry. It says that they want us to write down the KEQ4 in terms of K step 2 and K step 3. Okay? So you have to find the relationship between this, and this. So I don't know if anyone is able to spot it straight away. Can anyone spot it? Okay, next hint. Do you see that CH3NH2 to the power of 4 here is this one? Okay. And then do you see that CdCH3NH2 4H2O2 2 plus is this thing here? Okay. Okay. Still cannot spot? Next hint. Belum, can anyone spot yet? The answer is basically K step 2, K step 3. Okay? The answer must be that, not this whole thing. They're not interested in this formula. Another hint? Okay, next hint. Yes? Mana? Purple ni ka? This is not K step, but the equilibrium constant for equilibrium 4. Yes, correct. This is the equilibrium constant for this reaction, the one that I'm highlighting now. So basically, I want to transform this into something shortcut later on. Eugene, can you spot caution? This one ka? It's not it's not a stability constant. It's an equilibrium reaction. Tapi it's not stability constant, but it's a equilibrium constant. Yeah, just the normal equilibrium constant. Okay, next hint. Do you see En to the power of 2 here? En to the power of 2 here? And then CD close, getting warmer. I think it was Lim's answer. Siapa kanto? CdN2 H2O2 2 plus. Can anyone see it? K step. Close. You're going there, but not correct yet. Sorry, Ayman? Yes, it's K step 3 over K step 2. Okay? So I'm going to show you that how okay? So I'm going to take my K step 3. Okay, this is my K step 3. Copy. So just now Ayman said K step 3 times by 1 over K step 2. Okay? 1 over K step 2 is just inverting, right? Changing the position. Okay, so let's do that. Times by my CdH2O6 goes up. CH3NH2 to the power of 4 over this whole thing. H3NH2 4H2O, 2 plus. Okay, so I'm going to highlight sahaja just in case in case you cannot see it. Can you see that the CdH2O6 2 plus cancel out? Okay, so that means the answer is K step 3 over K step 2 for 1 mark. I don't know how else to show you a quick way for that. Okay, if you find out and if you would like to share, please share with us. Okay, but for now, that's the only method to see and to show you how equilibrium 4 is equals to K step 3 over K step 2. So the final answer that they are looking for is, I'm using the space here, K step 3 over K step 2. So that's writing down the expression in terms of that. So they don't really want the whole formula written down and whatnot. They want you to substitute K step 2 and K step 3. Okay, so if you're wondering what this is 1 over K step 2, and this is K step 3. Okay. Can see? Do you want me to zoom in lagi? Next question will be question 37, part C. For those of you who have finished copying this and is happy, if you're not happy, please don't throw your anger to me. This is all Cambridge. Daniel, okay? Sampit. Yeah, the bottom page, page 21, I had to do 2 in 1. Otherwise, this paper would be berapa pages niya? How many pages do we have? 50 plus, 48, 49. Yeah, that's why I have to do 2 in 1. Sorry about that. Yes? Hmm. Okay, step 3 over okay, step 2, yeah. That's the final answer, okay? That's what I was saying, that I don't know any other quick way to show you to get to this final answer. All right, for those of you who are happy, who's happy and or who don't care about this because they're planning to just skip it, sometimes in this case you can skip that question, but sometimes you need this expression to move on with other questions, okay? Question 37 now, part C. So you are given the structure of picolinic acid, the conjugate base. Okay, so I don't know if you still remember your old friend, acid, conjugate base. So they say conjugate base of this thing is a bidentate ligand. Okay, so that means two dative covalent bonds per molecule. Now, what is the conjugate base of picolinic acid? What happens, or how do we find? What about the H plus? Do we gain or do we lose the H plus? We lose the H plus, that's right. Acid will give away its H plus in aqueous solution. So the H plus that we're going to lose is the one that is attached to the COOH, okay? So then we form a conjugate base that looks like this. The rest of the molecule is the same, CO2 plus H plus. What about the charge of my conjugate base? If I'm neutral, I lose something positive, I become negative. Okay. Another way of looking at this is on the left side, you've got a neutral charge, and on the right side, minus, plus, neutral, balance. Okay. So this is my bidentate ligand. I am guessing, I don't know because I've not seen this ligand before. I'm guessing that the dative bonds are formed here where the nitrogen is and on the oxygen. Okay, I'm guessing, but I could be wrong. Define, I don't want to define, draw the structure of Z. Well, I've already shown drawn the structure of Z here. This is Z. The next one. The next one is what I want to look at. Not define the term. You know that I don't like definition question. Part 3, part 3. There's the structure, which we already have done. Part 3 said that Z reacts with chromium ions in 3:1. That means I need 3 molecules of Z to react 1 unit of complex ions to form a new neutral complex. Okay. Since Z is bidentate, so 2 dative bonds form. If I have 3 molecules of Z, how many dative bonds am I forming? 6. So that means my coordination number of the new complex would be 6. I do not have any water left in my formula. Okay? So that means my new formula is chromium with 3Z plus 6H2O. I kick out all the H2O. Well, they don't ask for the equation, but I thought that it's best to show you. What is the overall charge? Chromium is plus 3. Z is minus 1. So 3 times minus 1. Oh, neutral. It's mentioned. That's right. Thank you. Neutral. So that means no charge. CrZ3. State the coordination number. So you already know that 1 molecule of Z forms 2 dative bonds. 3 molecules would form 6 dative bonds. Geometry is the shape. It's octahedral. Okay, if you're done with that, the last question of the day would be question 38, part D. Question 38, part D. Okay. Right. So my diagram is cut off. Here is such a bad. See. Okay. The structure of chromium with there are this time the complex has 2 chromium centers. Okay. And then other 4 ethanoate ligand. Ethanoate ions act as the ligands in this complex. Okay, so if you're wondering how it looks like this. COO minus with a CH3. And then These two oxygens are the one that forms the dative covalent bond. So instead of writing this double C, CH3, whatever, they have used a shortcut to show just like that. Okay, and the rest of the molecule is just hidden in that formula. So that's why it is written like that. This is also for ethyl En. Sometimes En is written down like this as well. Sorry, not NH3. NH2, NH2. So our only interest is in the atom that forms the dative covalent bond. The rest of the molecule does not form any dative bond to the metal center, so that's why we just hide them. Okay? Right, let's look at our structure. I'm just going to use this bottom half of my diagram, okay? Water and ethanoate ions. So this is my water molecule. My